Several of you have mentioned having difficulty with the rational functions, which is in Unit 3, I believe, Lesson 3.1. And one thing that I'll direct you to is if you go to Lesson 3.1, Rational Functions and Their Graphs, and scroll down, you'll find the instructor-created videos and resources. And at the moment, there are not any videos, but there is a Word document which really gives you an outline of rational functions. It gives you the definition, some of the general characteristics, how to find the domain of a rational function, how to find the y-intercept, how to find the zeros, and then it gets into a discussion of the vertical, horizontal, and even slant or oblique asymptotes. And so I want to walk through a couple of examples with you. Primarily in Newton, you're asked to find the vertical asymptote and or the horizontal asymptote, but I also want to address, while we're looking at this, how to find the y-intercepts, the domain, and the x-intercepts. So typically, one of the first questions that's asked about a function is its domain. And one of the things you have to remember is a rational function looks like a fraction. And we know that for a fraction, the denominator cannot be 0 because division by 0 is not mathematically possible. So I have to determine what values for x are going to cause that denominator to be 0. So you have to remember in finding the domain that the denominator cannot equal 0. So in this case, we would have our denominator, which is x cubed minus 5x squared minus 14x, as a common, as in the denominator not equal to 0. And because I have an exponent of 3 there, we're probably going to have to factor in order to find those restricted values. So one of the things that I notice as I'm starting to think about factoring this is that I have a common factor of x. So I'm going to factor it out. So I would have x squared minus 5x minus 14. And we know that cannot be 0. Continuing with my factoring, I have x is going to tag along, and then I'm going to break down the quadratic that's inside the parentheses. I would have x times x. I need a pair of numbers that multiply to 14 and subtract to 5. I believe that would be 2 and 7. And I want to end up with a negative 5, so the 7 is negative and the 2 is positive. And so then I know that one of those pieces, either x was equal to 0, x plus 2, or it really cannot be 0, x plus 2 cannot be 0, and then x minus 7 cannot be 0. And so if I solve each of those respectively for x, the first one's already solved, so x cannot be 0. I would have subtract 2 from either side, so x cannot be negative 2. And then plus 7, x cannot be 7. So I've found the restrictions on my domain, but while finding the restrictions on the domain, I have also found the location of the vertical asymptotes. Okay, so if I write my domain in interval notation, and again, you may want to look at it on a number line. you would have holes at -2, 0, and 7, but you can choose any number to the left, between, or to the right. So my domain is going to have several pieces, goes from -infinity to -2, step over the hole, from -2 to 0, step over the hole, from 0 to 7, step over the hole, from 7 to +infinity. And again, what I've done, where those holes are located, while finding the restrictions on the domain at the same time, I have found the vertical asymptotes. The vertical asymptotes occur at the restrictions of the domain. And so if you were finding them kind of from the beginning of the process, again, you would set the denominator equal to 0 or not equal to 0 and find those restrictions. So I have a vertical asymptote at 0, at -2, and at 7, and they're vertical lines, so they're written in a vertical line format, which is always x equal to the number. Okay, so you really are doing two things at once when you set your denominator equal to 0. You're finding the restrictions on the domain, but at the same time, those restrictions become your vertical asymptotes. Then let's think about for just a minute how to find the y-intercept. The process for finding the y-intercept for any function is to let x equals 0 and we solve for y. So if I go back to the original function and I'm substituting 0 in place of x, I would have 0 squared plus 7 times 0 over 0 cubed minus 5 times 0 squared minus 14 times 0. So doing the calculations, I would have 0 plus 0 over 0 minus 0 minus 0, which gives me 0 over 0, which we know really can't happen. So in this particular case, this particular graph would not have a y-intercept. Now that's not always the case, it just happens to be the case here in this particular problem. Let's look at how to find the x-intercepts or the zeros. Okay, so to find the 0 or zeros, which are also known as your x-intercepts, again, we really would let y equal 0, but there's a shortcut for a rational function, and that is you take the numerator and set it equal to 0. Okay, so if I take my numerator, which is x squared plus 7x, and I set it equal to 0, and then I want to solve for x. Again, because I have a squared term here, it's likely that I'm going to have to factor. I have a common factor of x. I'm left with x plus 7 equal to 0. I know that one of those pieces, either x was equal to 0 or x plus 7 was equal to 0. Again, we're trying to solve for x. The first piece is already solved for x and would give us the ordered pair 0, 0. But we also determined earlier that you couldn't have a value for 0, so really this is kind of an extra solution. Then we're going to solve the other one. So we subtract 7 from either side and we get x equals -7. So as an ordered pair, you would have -7, 0 as your x-intercept or your 0. Finally, we would talk about the horizontal asymptote. Now, it's a little bit more challenging to decide or determine your horizontal asymptote because you have to compare the degree, which remember is the highest exponent of the numerator, to the degree of the denominator. So you're going to compare the highest exponent in the numerator, which is the top, to the highest exponent in the denominator, which is in the bottom. And there's three possible options. The degree of the numerator could be less than the denominator. The degree of the numerator could equal the denominator, or the numerator could be greater than the denominator. If the numerator is less than the denominator, there is a horizontal asymptote at y equals 0 or the x-axis every time, all the time. If the numerator is equal to the denominator in degree, then there is a horizontal asymptote at y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. It's called the ratio of the leading coefficients. If the numerator is greater than the denominator, there is no horizontal asymptote. There could be an oblique or slant asymptote, but your particular lesson does not discuss the slant or oblique. Okay, it only focuses on the horizontal. So again, if I go back up to the beginning of my problem, the degree in my numerator, okay, the degree of the numerator, which is the highest exponent, is 2, and the degree of the denominator is 3. So if I compare those two numbers, 2 is less than 3. So since 2 is less than 3, I know there's a horizontal asymptote that will occur at y equals 0, which is the x-axis. Now, sometimes the graph may give you some insight into this. Sometimes it doesn't because of the asymptotes, it sometimes will do funky things. But if we put this into our graphing calculator, and you would need to put parentheses around the numerator and denominator, we would have parentheses x squared plus 7x, close them, divide by parentheses x raised to the third minus 5x squared minus 14x, and close the parentheses, and then graph. Okay, and you kind of get these three curves, and if you'll notice, it's a little hard to see, but there's a little bit of a break or a hole, a gap there at 0. You can kind of see that the graph is broken, because remember, you can't have a value at 0. Okay, so just be careful of that. You can kind of see that there is a line here at -2 and one at +7 where you have your vertical asymptotes. Okay, so sometimes you may need to simplify your radical first, or your expression first. I didn't do that on the other problem. I probably should have, but I didn't. Okay, so let's see if we can simplify this first by factoring. Okay, so if we factor this, the first one, the top is a perfect cube. So we would have f of x equals x minus, let's see, 81 would be No, maybe it's not a perfect cube. Okay, let's see. What is the cube root of 81? I don't remember that one off the top of my head. Okay, it's not a perfect cube, so that one doesn't factor. Although the denominator does factor, okay, it's not really going to help us a lot because the numerator doesn't factor here. But oftentimes you should think about trying to simplify your function first. Okay, so let's see. My computer's going crazy here. It doesn't like the fact. Okay, so let's think again about finding the domain of the function. And again, to find the domain, which does lead to the vertical asymptotes, I would take, and this thing is doing something crazy, I would take my denominator, x cubed plus 7x squared minus 18x, and I'm going to solve it for x. And for some reason, my tablet is doing something funky. Let's see if I can get it back on track here. Okay, so my domain, let's see, wants to do something crazy, so we'll just scroll on down to a new page maybe. Okay, so our domain is, we got to make sure that x cubed plus 7x squared minus 18x does not equal 0, because you cannot divide by 0. So again, because I have an exponent of 3, my first thought is, let me see if I can factor this. And I notice again that I have a common factor of x. So I have x squared plus 7x minus 18, and that cannot be 0. Then I'm going to try to factor the quadratic. So I'm going to break it down. I have x and x, pair numbers, multiply to 18, subtract to 7. That would be 2 and 9, positive 7, and a minus 2. And again, they cannot be 0. So that tells me that one of these pieces, either x was equal to 0, x minus 2 cannot be 0, or x plus 9 cannot be 0. And if I solve each of those individually for x, the first was already solved. Add 2 to either side. So x cannot be positive 2. And then the last one, I'm going to subtract 9 from either side. So x cannot be negative 9. So again, I've found my restrictions, and you may want to take a look at those restrictions again on the number line to help you write the interval notation. We have 0, 2, and negative 9, and you're going to have holes there. But again, you could choose anything to the left, to the right, or in between those numbers. You just can't choose those exact numbers. But also remember, those values become the vertical asymptotes. So my vertical asymptotes are x equals 0, x equals 2, and x equals negative 9. Writing your domain in interval notation, we would have from negative infinity to negative 9, step over the hole, from negative 9 to 0, step over the hole, from 0 to 2, step over the hole, from 2 to positive infinity. Again, if we think about our x-intercepts, or excuse me, our y-intercepts, we're going to let x be 0 and solve for y. So I would have f at 0 equals 0 cubed minus 81 over 0 cubed plus 7 times 0 squared minus 18 times 0. So we end up with negative 81 over 0. But remember, you can't have 0 in the denominator. We already figured out that 0 was a vertical asymptote, or is one of our restricted values. So here again, this particular graph would have no y-intercept. Then if I want to think about, I have to scroll back up, I've run out of space. If you want to think about your your x-intercepts, or your zeros, okay, so for our zeros, again, the shortcut is to take the numerator, which is x cubed minus 81, and set it equal to 0, and we're going to solve for x. So I'm going to add 81 to either side to isolate the x. So we have x cubed equals 81. Then we're going to take the cube root of both sides. Okay, so we have x equals, and x cubed, the cube root of 81, is not a perfect cube. It comes out to be approximately 4.33 if you round it to 2 places. If you wanted to break it down, it's going to become 3 on the cube root of 3 if you want it to be exact. Okay, so it kind of depends on how you're asked to express your answer. And then I'm going to go back and I'm going to think about my horizontal asymptotes. If I look at the degree of the numerator, which is 3, so the degree of my numerator is 3. The degree of my denominator is also 3. So the degree of the numerator is equal to the degree of the denominator. So my horizontal asymptote is going to be the leading coefficient, which is, remember, the number in front of the highest degree, which for the numerator would be an understood 1. It's also an understood 1 in the denominator. So I have a horizontal asymptote at y equals 1. Now again, you can take a look at this on the graph if you so choose. Okay, so let me clear this one out. Again, you would type it in with parentheses. You'd have parentheses x raised to the third. Whoops, I got the wrong. Parentheses, whoops, parentheses x raised to the third minus 81. Close the parentheses, divide, open a second set, x, right, oh my goodness, sorry about that. I keep hitting the wrong button. Raised to the third minus 81, close them, divide, open. I'd have x raised to the third plus 7x x squared minus 18x. I keep hitting the wrong button. Oh my goodness, guys. X, I forgot to put my parentheses in there. X raised to the third minus 81, close them, divide, open, x raised to the third plus 7x squared minus 18x. Close them. Finally, sorry about that. Okay, graph. And there you have your picture. Did I enter that correctly? Let me see. Oh, sorry, I left out my minus sign here. Okay, now let's graph it. I knew I had something wrong. Okay, so you actually have 4 different pieces here, and you may have to zoom out to see them all. Okay, so on our graph, again, we want to zoom out so that you can kind of see all the pieces. And again, notice how it has this break here around the origin. Okay, so hopefully that'll help you in terms of rational functions, at least to help you find the vertical asymptotes and the horizontal asymptotes.